Now let's look specifically at two-port networks. Two-port networks are very common in engineering and microwave engineering. Essentially, they're a device where some signal comes into an input port, and that signal then comes out of the output port, and that two-port device then does something to the signal. It can filter it or amplify it or do any number of things to that signal. And so oftentimes we want to isolate a two-port device, and to understand what it does, we need to look at the condition of the signal or the power coming in as opposed to the condition of the signal or the power coming out. And so to do that, we frequently describe the two-port device in terms of its transimpedance parameters. If we're talking about its insertion in a system where the sources are time harmonic or sinusoidal, like we are assuming in radio engineering. So to understand the effect of a two-port device in a microwave system, we are going to use a slightly different model than simply talking about an equivalent source or an equivalent load. We want to isolate the two-port device that we're interested in, and then everything to the left of that two-port device from where energy is coming, we're going to group that into one device, and we're going to call that the equivalent source. On the other side, on the output side of this two-port device that we're interested in, we're going to take everything downstream toward which the energy is flowing, and we're going to group that together in a box. And if the devices are linear time invariant, we can characterize it with its input impedance, and so we call that the load. The input impedance is a load impedance for this particular circuit. And so we're going to, again, talk about the device and how it behaves in terms of the signal coming in, its signal power, the power delivered from the source, and in terms of the power coming out of the two-port device, and that power, therefore, is absorbed by that load. So as we've talked about before, everything to the left of the input of that two-port device, we're going to group in something called the source, and the source is just the device from which energy is flowing at a certain rate, and so we call it the source power, or specifically we are concerned with the power delivered by that source. Everything on the output, connected to the output of our two-port device, again, we're going to group into an equivalent circuit, which is the input impedance, and that is the load, and that will absorb energy. And so there's a rate of energy flow that we call the absorbed power, the power that's coming out of the two-port device and therefore being absorbed by the load that its output is connected to. This type of equivalent circuit, then, is one that we use quite often in radio engineering to examine the behavior of a two-port device. We have an equivalent source, which models, again, the circuit from which the energy is coming, and an equivalent load on the other side. If we know for example, the impedance matrix, the transimpedance parameters, 4 of them in the case of a two-port device, then we can go through and solve this circuit, analyze the circuit, and we can determine things like the voltage and current at the input port and the output port. And of course from that we can determine the rate at which energy is flowing across this plane, being delivered by the source, and likewise determine the rate at which energy is flowing across this plane and thus being absorbed by the load. So we count up the number of unknowns here. We have 4 unknowns that we have to solve for, and it turns out we're going to have 4 equations. One equation for the Thevenin's equivalent source, one equation for the load, and then of course 2 equations that come from our transimpedance parameters. So with our Thevenin's equivalent, we can go through and apply KVL and Ohm's law and relate the current I1 to the voltage V1 using this expression. And it's important, again, that we use the notation to come up with this, otherwise we'll get incorrect signs. So we define positive current as flowing in this direction, and so we have Vg minus the voltage drop across this impedance will provide the value of V1. We arrange that KVL and we get this result here. Of course, we could write this equation, rewrite it in terms of V1 equal, in that case, to Vg minus I1 times ZG. Same equation, just rearranged, and so we could use it either way. Similar to Ohm's law, we can write Ohm's law in terms of current, or we can write it in terms of voltage. Current is voltage divided by impedance, or voltage is current times impedance. In this case, we'll write it in terms of I2. Once again, we have to be very careful here with the minus sign. When we look at this, I2 is positive when moving into the 2-port device, into port 2. That's positive current, and of course that means the positive current is positive when coming out of ZL. And so this is the different notation that we use for Ohm's law. For Ohm's law, we could have V2 equal to VL, and then we would have IL, the current flowing into the device, of course, is the opposite direction of I2, or more specifically, what we call positive current is in the opposite direction of I2, and thus we have a minus sign. Essentially, we're using KCL to say that I2 is equal to minus times IL. And so that's where the minus sign comes in. So this is a frequent error that students make when they try to use transimpedance parameters to solve circuits. They write equations that are not consistent with the notation. And again, we have to go through and use our current and voltage notation this way. Positive current is always defined as flowing into the multiport device for which we have our transimpedance parameters. So the previous slide gave us two equations, one equation from the Thevenin's equivalent, one equation from Ohm's law. We have 4 unknowns, however, 2 voltages, 2 currents, so we know we need 2 more equations. And of course, we get those 2 equations from the transimpedance parameters of our 2-port device. If we have that knowledge, we can write equations that relate voltage V1 to each of the 2 currents, I1 and I2, and likewise voltage V2 in terms of current I1 and I2. These are the components. This term is the first component of V1, and this second term is the second component, the component of V1 that is due to I2, for example. So I put them all together. We have 4 equations. We have 4 unknowns, 4 complex equations. And we can go through and do our algebra and find the result for each current and each voltage. These then, collecting them, are the 4 equations that we have for the previous circuit, 4 equations, 4 unknowns, and we just sprinkle some algebraic pixie dust on our equations and do a little work, and we can get the solutions for each of the currents and voltages. So we do algebra and we get these results, 2 currents and 2 voltages. I'm going to go through and do some sanity checks. First of all, we want to make sure that the equal sign is similar on either side, or the type of value on either side of the equal side is similar. Notice I1 is a complex number. It has a real and imaginary part, or magnitude and phase. And everything on the right side, all the variables are complex, and so the result will be complex as well. We have a complex value is equal to a complex value. Now, it's important that you think about what this means. When we say 2 complex numbers are equal to each other, what we're saying is that the real part of each of the 2 must be precisely equal to each other, and the imaginary part likewise must be precisely equal to each other. We cannot have 2 complex numbers that are equal to each other in some way, even though the real values are different or the imaginary values are different. If we say they're equal, both the real and imaginary parts are the same. Likewise, if we write them in terms of magnitude and phase, 2 complex numbers that are equal must have exactly the same magnitude and precisely the same phase. And so in this case, we find we get complex numbers on either side of our equal sign. So there's sanity check number 1. Sanity check number 2 is to go through and make sure we have a dimensional analysis that is correct. So we have amps here, and if you go through and look at the right side, numerator we have impedance, denominator we have impedance squared. And so this term here becomes 1 over impedance, so we multiply that by voltage, we get voltage divided by impedance, and of course that has units then of current. Likewise, for the second term that we get here, we find by similar analysis get that the units are amps for I2. For the 2 voltages, we look here, we see we get a VG out front. So this remaining term here with all these impedances must be a coefficient, must be unitless, must not modify the voltage in any way. And it turns out it does, because we look in the numerator, we get units of impedance squared, and likewise the denominator, units of impedance squared. So the impedance squareds cancel out, we just get a coefficient that does not modify the volts, and the result then is V1 in volts. The same thing for V2 when we go through and look at it. This term involving all the impedances, impedance squared divided by impedance squared, and therefore the units of V2 are volts, as they should be, as they must be. Finally, one last sanity check that we look at, and we see how many variables there are in our circuit. We have VG is 1, ZG is 2. We have 4 transimpedance parameter, that makes 6, and then ZL is 7. 7 different parameters, 7 different complex numbers parameterize this circuit. And when we look at each of these results, both currents and both voltages, they are dependent on all 7 of those parameters. In other words, every element of the circuit will affect each current and each voltage. None of the currents or voltages are independent of any of the 7 values that parameterize this circuit. Now, that doesn't always have to be true, but if it turns out not to be true in your analysis, again, that gives us pause. Why is our result not dependent on all the elements of the circuit? In this case, it is. And again, that makes us feel that perhaps our analysis is correct. Again, sanity checks don't tell you for sure that it's correct, but if it does not pass the sanity check, you know for sure that it is incorrect. So it's always important to go through and do this analysis. Now, look in the title here. I said, apply the sanity check, and I say, then forget them. What do I mean? I'm saying, forget these results here. If you ever use these results to solve a problem in this class, you're doing something wrong. The reason we did this is to show that the transimpedance parameters for this 4-port device, in addition to the the equivalent circuit for the source and the load, are sufficient to determine the current and voltage. We know exactly what they are from just these values, these 7 parameters. And once we know the currents and voltages, we can determine the power flow across each of the planes, the rate of which energy is being delivered by this equivalent source and absorbed by this input impedance, this equivalent circuit ZL on this side. So we have the parameters to get all the answers we want. Yes, we could take these values and stick them in here and do some calculations and get the answer, but that's not how we want to do it in this class. It turns out there's a simpler way of determining, for example, the value of I1 and V1, one that's more physical and more intuitive in terms of the result and doesn't require you to tire out your finger pushing buttons on your calculator. So once again, don't ever use these equations for finding an answer. If you're using these equations to determine values of V1 or I2, for example, then you are doing something wrong. Stop and figure out a different way, an easier way to get the answer.